We're going to talk now about doing some calculations for solutions. So this was mentioned briefly before, but we need to recognize what molarity is. So molarity is going to be equal to the number of moles of solute per 1 liter of solution. So an example we looked at, if we have 7.25 grams of magnesium chloride dissolved in 127.5 milliliters of water, we want to know the molarity of the magnesium chloride in solution. So the magnesium chloride is a solute, water is going to be the solvent, combined that's going to be the solution. So magnesium chloride is going to be the solute, and I'm going to need to figure out the moles of solute. So I have 7.25 grams of magnesium chloride. Use the molar mass to convert to moles of magnesium chloride, and I get 7.61 times 10 to the negative 2 moles of magnesium chloride. Now that I know the moles of the solute, put the moles of the solute over my milliliters of solution. But now keep in mind it has to be over liters of solution. So I've got to convert my milliliters to liters. And so when I carry out that calculation, I end up with 5.97 times 10 to the negative 1 moles of magnesium chloride over 1 liter of magnesium chloride solution. That then is my molarity, and what I can do is write that out in a simplified version, just 5.97 times 10 to the negative 1 capital M magnesium chloride, or 5.97 times 10 to the negative 1 molar magnesium chloride. Now if I take that same problem and just modify it a little bit, and let's say I want to look for the molarity of the chloride ions in solution. So now the solute I'm interested in is chloride ions, so I need to find out how many moles of chloride ions I have. So it's 7.25 grams of magnesium chloride. Use the molar mass to get to moles. Do my mole-to-mole conversion. And that'll tell me how many moles of chloride ions I have. Once I know the moles of chloride ions, take the moles divided by my volume. I got to make sure that volume's in liters. And I end up with 1.19 moles of chloride over 1 liter of the magnesium chloride solution, which can be represented by the 1.19 molar chloride. Okay, so all I've done is added that one extra step of converting from the magnesium chloride moles to moles of chloride ions. It still comes to that idea of moles of solute over liters of solution. It's very, very important to get that down with these molarities. Another approach of looking at this problem is that if I already knew my molarity of my magnesium chloride, and I'm looking for the molarity of my chloride ions, well, if I have the 5.97 times 10 to the negative 1 molar magnesium chloride, that's 5.97 times 10 to the negative 1 moles of magnesium chloride per 1 liter of magnesium chloride solution. That now is a conversion factor. So why don't I use that and start with that and then do my mole-to-mole conversion. Once I'm done with that, I get the 1.19 moles of chloride per 1 liter of magnesium chloride solution, or my 1.19 molar chloride. Either way works. The thing you need to start recognizing now is this molarity is going to be very, very important. And molarity is going to be used as a conversion factor that we're going to use all the time when dealing with aqueous solutions. A lot of what we're going to look at in chemical reactions is going to involve aqueous solutions, so you've got to recognize this molarity conversion. All right, let's look at another example. Let's say I want to determine the concentration of Cr3+ in a 3.68 liter solution that contains 6.73 grams of chromium 3 sulfate. All right, so I need my moles of solute. My solute in this case that I'm concerned with is chromium 3+. I'm going to start with my 6.37 grams of chromium 3 sulfate. Use a molar mass of that, convert to moles. Convert from my moles of chromium 3 sulfate to just moles of chromium 3+. And that gives me the 3.43 times 10 to the negative 2 moles of chromium 3+. Now I need to put that over my volume. Now in this case my volume is already in liters, so I don't have to convert it to liters. When I divide that out, I get 9.33 times 10 to the negative 3 moles of chromium 3 plus per 1 liter of the chromium 3 sulfate solution. or 9.33 times 10 to the negative 3 molar chromium 3 plus. What if I wanted to know the sulfate concentration? Well, I can still start with my 6.73 grams of the chromium 3 sulfate, use the molar mass to convert to moles, carry out my mole to mole ratio, and get the 5.15 times 10 to the negative 2 moles of sulfate. Take those moles, divide by the volume, and I get 1.40 times 10 to the negative 3 moles of sulfate per 1 liter of the chromium sulfate solution, or 1.40 times 10 to the negative 3 molar sulfate. Don't forget that zero. I need to have 3 significant figures, so I need to put 1.40. Also, again, I want to remind you that when I'm writing things out, I write out very specifically. I'm not just writing moles and grams and liters. Get specific in your units. All right, yet another type of calculation we can do with molarity, and this is actually going to involve preparing solutions. So let's say you want to prepare 1 liter of a 1 molar sodium chloride solution. How many grams of sodium chloride would you need to prepare this? Well, if we're going to measure out grams, grams tells us something we physically measure in the lab. What do we use to relate to the atomic or molecular level of things? Well, that's where we use the moles. So if I know I have a 1 molar sodium chloride solution, that's 1 mole of sodium chloride per 1 liter of sodium chloride solution. Now if I start with my 1 liter sodium chloride solution, I use that molarity now as a conversion factor. Then I take those moles of sodium chloride, convert to grams of sodium chloride using molar mass. I get 58.44 grams of sodium chloride. Now this calculation seems pretty straightforward, pretty easy, but that's because everything is a 1. Okay? Look at the setup. Pay attention to the setup. Think about that molarity again as being a conversion factor between moles of solute and liters of the solution. So this tells us how many grams of sodium chloride we need to make this solution. But now, how would we actually prepare this in a lab? We'd start by massing out the 58.44 grams of sodium chloride, and we put that in a 1 liter volumetric flask. We'd add enough water to get the solid to dissolve initially, and then we'd continue to add water until we reach that 1 liter mark on the volumetric flask. Then we ensure it's properly mixed, and we'd end up with our 1 molar sodium chloride solution. Okay, so we're going to take our solid, put some initial water in to dissolve it, and then add the rest of our water to get it up to the final volume we want. Okay, now that's using a volumetric flask. That's when you have exact volumes. Similar process though when we don't have perfect volumes where we can use volumetric flasks. Let's look at an example of that. So let's say I want to prepare 375 milliliters of 0.125 molar sodium chloride solution. How many grams of sodium chloride would I need? Not easy numbers this time that you could do in your head. So we've got to recognize that the 0.125 molar NaCl stands for 0.125 moles of NaCl per 1 liter of NaCl solution. Take the 375 milliliters of NaCl solution. We've got to get that to liters of NaCl solution. And then we can take the liters of NaCl solution to moles of sodium chloride using our molarity. And then we convert our moles of sodium chloride to grams of sodium chloride using our molar mass. And we end up with 2.74 grams of sodium chloride. So how would you prepare this in the lab? Well, this is a little bit trickier because there's not going to be a volumetric flask that has 375 milliliters. But it's going to be the same basic idea. We start by massing out the amount of solid we need, putting it in some container. Then we'd add 375 milliliters, measured out using like a graduated cylinder, and then we'd mix it. Okay? It's just because it's 375 milliliters, we have no volumetric flask where we could fill it just exactly to 375 like we do with the volumetric flask. We'd have to add that volume measured out. Okay, so that's how we prepare solutions. Those are calculations involved with determining what mass we need in order to prepare a solution of a certain volume and a certain molarity. Now another calculation that's going to be pretty common is starting with a known molarity and wanting to dilute it down to another molarity. All right, so we're going to use something called the dilution equation. Molarity of solution 1 times volume of solution 1 equals molarity of solution 2 times volume of solution 2. That's the dilution equation. So we're going to take and dilute a volume of V1, that's of solution 1, who has the molar concentration M1. We're going to take that volume, dilute it down to a new volume, volume 2, whose molar concentration is M2. All right, we're going to see a picture of that here in a second and run through some calculations, but a key thing you need to recognize here is, why can we set these two equal to each other? Why can we set M1 V1 equal to M2 V2? Well, let's say I have a molar sodium chloride solution, and I took a certain volume of that sodium chloride solution. When I multiply those out, I get moles of sodium chloride in solution 1. I then look at my new solution that I'm going to be making, which is going to be my dilute solution, and its molarity is going to be moles of sodium chloride per liters of sodium chloride solution times the liters of sodium chloride solution, and that'll equal moles of sodium chloride in that second solution, in that dilute solution. Well, based upon this equation, moles of sodium chloride in solution 1 are going to be equal to moles of sodium chloride in solution 2. Where am I getting all the moles for solution 2? It's coming from solution 1. All I'm doing is I'm changing the volumes. And by changing the volumes, I'm changing the molarities. That's what dilution is. And that's why we can set these things equal to each other. So a picture example of this, if I'm going to make 3 liters of a 0.5 molar calcium chloride solution, and I'm going to start with 0.15 liters of a 10 molar stock solution. 0.15 liters of a 10 molar stock solution will give me 1.50 moles of the calcium chloride. Once I've got that 0.15 liters, all I'm doing is I'm adding enough water to get me to a total volume of 3 liters, but I haven't added any extra calcium chloride. All I've done is just added water. Which means when I get finished, when I have the 0.5 molar calcium chloride and I have 3 liters of it, the number of moles in that new solution should equal the number of moles in my original solution that I started with. That's what the dilution equation works around. And you have to understand that. Right? When it comes to solution stoichiometry and doing some acid-base calculations, a lot of people have decided to use M1 V1 equals M2 V2. We're going to go through those calculations. Do not use it there. M1 V1 equals M2 V2 only for dilution calculations. Okay, that's the only time you should be using it, is just for dilution calculations. All right, let's look at another example of this. So if I take 125 milliliters of a 0.751 molar sodium chloride solution, and I add enough water to get that to 275 milliliters total, what's the concentration of the new solution? So I have 0.751 moles of NaCl over 1 liter of the NaCl solution 1 times its volume in liters, and that's going to be equal to the volume in liters of solution 2, my dilute solution, times the molarity of solution 2. Well, that's where I don't know the molarity, so I'm trying to determine what M2 is. So, plug those in, solve for X, I get 0.341 moles of sodium chloride per 1 liter of sodium chloride solution 2, or 0.341 molar sodium chloride solution. I went from 0.751 molar to 0.341 molar. I diluted it. I got a lower concentration. An easier way of looking at this calculation, I can just take my molarity directly and multiply it by its volume in liters. That'll be equal to my new molarity of my dilute solution times the volume of that dilute solution. I'm still going to end up with the same value. So let's take a look at another example of this type of calculation. Let's say we want to create 325 milliliters of a 0.123 molar potassium nitrate solution. And we have a 0.53 molar potassium nitrate solution to work with. Well, we're going to have to dilute that solution down. So we need to know how many milliliters of our concentrated solution, we need to dilute down to 325 milliliters to get to that 0.123 molar potassium nitrate. So let's set this up. Got my 0.453 molar potassium nitrate solution 1 times the volume that we're going to try to determine of that potassium nitrate solution 1. And that should be equal to the concentration of the dilute solution I want to make, the 0.123 molar, times the volume of that dilute solution. So when I solve for x, I get 8.82 times 10 to the negative 2 liters of the potassium nitrate solution 1, or I'm going to change that into 88.2 milliliters of potassium nitrate solution 1. So now we know how much of that concentrated solution I need, and I'm going to take that volume of the concentrated solution, I'm going to add enough water to dilute it to 325 milliliters. So how much additional water am I going to need to add to that 88.2 milliliters? Well, I know I want a final volume of 325 milliliters, so I just want the difference between those. So if I take 88.2 milliliters of solution 1 and I add 236.8 milliliters of water, that will give me a total volume of 325 milliliters. So the potassium nitrate is coming from solution 1, and the moles of potassium nitrate from solution 1, all of those moles end up in solution 2. It's just we've added more water, we've got a larger volume, we've diluted that concentration down. Alright, so that's it for solution calculations, but you're going to see these calculations a lot more.